This is part 1 of the video introduction to Activity 3.3, Algebra Pieces and Quadratic Functions. In this activity, we'll learn to use algebra pieces and symbolic steps to find the key features of quadratic graphs, such as y-intercepts, x-intercepts, and turning points. We'll learn about the factored form of a quadratic function and its relationship to the x-intercepts of a parabola. And we'll use algebra pieces and corresponding symbolic steps to find points of intersections between the graphs of functions. We'll use our full set of algebra pieces, black and red tiles, white and opposite white x strips, and black and red x squares. Since a quadratic function is a polynomial of degree 2, we can think of all quadratic functions as having the form y equals ax squared plus bx plus c, where the coefficients a, b, and c are real numbers and a is non-zero. We want to find the important features of quadratic functions. You may have noticed that the important features of the parabolas graphed in Activity 3.2 were easy to find. For many quadratic functions, the important features may not be so obvious. Let's consider the extended tile sequence from question 4 in Activity 3.2. Here's the sequence, and you can see figure x is x squared plus x. To find the y-intercept, you have probably observed that you can use the x figure or the x equals 0 figure of this and any extended tile sequence to easily determine the y-intercept. Looking at the x figure here, we see no individual black or red tiles, and looking at the x equals 0 figure, you can see here it's blank. We see that when x equals 0, the y value is 0. Thus, for g of x, the y-intercept is 0, 0. We can find x-intercepts with edge sets. The x-intercepts on any graph are the points where the graph crosses the x-axis and the y value is 0. One way to determine the symbolic formula g equals x times quantity x plus 1 for this sequence is by looking at the edge sets of the x figure. We can also use these edge sets to find the x-intercepts. The first step for finding the x-intercepts of any function is to set the function equal to 0. That's the y value of the x-intercepts. So in this case, x times quantity x plus 1 equals 0. In Chapter 1, we learned that an array of black and red tiles has net value 0 only if at least one of the edge sets of the array also has net value 0. The x figure of y equals g of x is rectangular, and therefore it is an array. The array representing g of x can only be equal to 0, have a net value of 0, if one or both edge sets have a net value of 0. Therefore, to find the x-intercepts of g of x, we set each edge set equal to 0 and solve. We obtain x times quantity x plus 1 equals 0. Thus x equals 0 or x plus 1 equals 0, which yields x equals 0 and x equals minus 1 as the x values for the x-intercepts of g of x. Here's a picture of the x figure with the edge pieces. You can see there's x down the left and x plus 1 across the top, and the corresponding symbolic steps for finding the x-intercepts. How do we find the turning point? In Activity 3.2, we observed that when the graph of a quadratic function crosses the x-axis, the turning point of the function is halfway between the x values of the two x-intercepts. In this case, the two x-intercept x values of g of x are x equals -1 and x equals 0, and the halfway point between these two x values is x equals negative 0.5. Evaluating the function g of x at x equal negative 0.5, we have g of negative 0.5 is negative 0.25. Thus, the coordinates for the turning point for g of x are negative 0.5, negative 0.25. Here's a graph of g of x with those key points labeled. When the graph of a quadratic function does not pass through the x-axis, we will develop additional methods to determine the location of the center turning point. When we do this work, we set an array equal to 0 and only 0. We can only find the x-intercepts and solve equations using the edge sets of a rectangle if you have an array set equal to 0. For example, if an algebra piece model is organized as x squared plus 6x equals negative 9, we must first move all the pieces to one side of the equal sign before proceeding. In this case, this would look like x squared plus 6x plus 9 equals 0. This matches our previous work with arrays, where non-zero net value arrays may have a variety of edge sets without the benefit of at least one edge set must be equal to 0. When looking at x squared plus 6x equal to negative 9, negative 9 might be modeled with any of these non-equivalent arrays. A 1 by negative 9 array, a negative 1 by 9 array, or a 3 by negative 3 array. With all of these options, it does not make sense to try to solve x times quantity x plus 6 equal to negative 9. It does work to solve x squared plus 6x plus 9, which is quantity x plus 3 times quantity x plus 3 equal to 0. In our previous discussion, the function y equals g of x can be written in two ways. G of x equals x squared plus x, or g of x equals x times quantity x plus 1. The second method is called the factored form of g of x. Similarly, y equals quantity x plus 3 times quantity x plus 3 is the factored form of x squared plus 6x plus 9. The idea of factoring a quadratic function and finding the x-intercepts of a quadratic function go hand in hand. Can you see why? There's more to think about when we look at non-rectangular x figures. See the second prep video for a review of these details.